Hello everyone, my name is Rishabh Bafna and I work as faculty at ACE Engineering College, Hyderabad. Apart from that, I work with ACE Academy as well. So in this video, let's get started with memory management topic from operating systems. So before starting everything, I'm asking you a question. What do you mean by main memory and what do you mean by secondary memory? See, main memory is also called as primary memory, which is also called as physical memory. That is what you call as RAM. Next one, this secondary memory. Secondary memory is also called as logical memory, is also called as virtual memory, and it is also called as ROM. Now, if you observe, secondary memory means your maybe hard disk, maybe SSD, isn't it? Mostly, main memory, that RAM, will be faster as compared to your secondary memory. You must have observed it. Let's get to next point. See, what is functionality of memory management? Allocating and deallocating memory to the processes. We are allocating and deallocating memory to the process. Let's see goal. Efficient utilization of memory by minimizing the internal and external fragmentation. These are the points which you will encounter in further slides. Internal and external fragmentation. What is it and why do we have to minimize it? Okay. So I'll tell you when that particular point comes. Let's see next one. Memory representation. See, memory is represented in two different ways. First one, word addressable memory. Second one, byte addressable. Word addressable means it will be in words. For example, let's say 128 kilowords. That is 128 kilowords I have mentioned here, okay? Or 1 gigawatt, something like this. It is in words. Now next one, okay? I think. Next one, byte addressable memory. For example, 128 kilobytes. That is 128 kilobytes. I have mentioned it. Just see here. It is ending with capital B, bytes. Let me just turn on that ink. 128 kilobytes. Fine. So 1 byte is equal to 8 bits. See, 1 byte is equal to 8 bits. Now, if the memory is word addressable, okay, 1 word equal to how much? That should be stated in the question, isn't it? Is either 1 word equal to 1 byte or 2 bytes or 4 bytes, okay, whatsoever it is, it has to be stated in the question. Now, next one. Let's see, few things which you need to know before getting started. Okay, this is very basic, okay. 2 raised to 0 equal to 1, 2 raised to 1 equal to 2. It should be at your fingertips, okay. You should be able to calculate fastly. 2 square 4, 2 cube 8, 2 raised to 4 16, 2 raised to 5 32, 2 raised to 6 64, 2 raised to 7 128, 2 raised to 8 256, 2 raised to 9 512. Okay. Next comes 2 raised to 10, which is 1024. Okay, you will be calling it as 1k. Okay, just note this one k. When it is 2 raised to 10, you'll use k, kilo. Okay, next one. 2 raised to 20, mega, 1 m. Next one. 2 raised to 30, giga, 1 g. 2 raised to 40, tera, 1 t. 2 raised to 50, peta, 1 p. I hope you are getting it, okay. When it is 2 raised to 10, use k. When 2 raised to 20 is encountered, use m. When 2 raised to 30 is encountered, use g. 2 raised to 40, use t. 2 raised to 50, use p. I hope you got it. Now, one interesting thing which I have noticed is, see, whenever you get something like this, let's say 256, what most of the students will do, they'll start counting from first, okay, 2 raised to 1 is 2, 2 raised to 2 is 4, 2 raised to, 3 is 8, so on, they'll keep on counting till they encounter 256. Now, instead of doing it, okay, if you get habituated to this so much, then at that instant itself you will get, okay, 256 is 2 raised to 8. One shortcut which I can tell you is 2 raised to 6. 2 raised to 6 is 64. So you can just map 6, 6. 2 raised to 6 is 64. If at all someone say 128, okay, 2 raised to 6, 64, it will be 2 raised to 7. Directly you can say it, okay, done. That's it for this one. See, let's have a look at this question. What is the capacity of the following represented memory? Now, this is the memory which is represented. Okay, 0, 1, 2, 3, 4, 5, 6, 7. If you observe it, there are how many words? 8 words. 0 to 7, 8 words in the memory. And each word is of what? 16 bits. It means 2 byte. Okay, this one is of 16 bits. This entire thing is of 16 bits. 16 bits means what? I told you initially, 1 byte equal to 8 bits. So 16 bits means what? 16 by 8, that is 2 bytes. 2 bytes. There are 8 words, each word is of 2 bytes. So what will be the capacity of the memory? 8 into 2 bytes. Obviously 8 to the 16 bytes. Just have a look at this. Capacity equal to number of words in the memory into word size. Just have a look at this one. Number of words, how much words are there? Obviously 0 to 7, it means 8 words are there. Next one, into word size. What is word size? 16 bits. So 16 bits. So just convert it into bytes. Okay, 8 into 2 byte. 8 to the 16 byte. Done. Capacity of the memory is 16 bytes. Next one. Consider the system with 512 gigawords. Okay, G is mentioned here. I hope you got to understand what is G. Initially I mentioned everything. What is G, what is K, what is P, what is T, etc. etc. Okay, what is M. Now 512 gigawords. Consider a system with 512 gigawords and each word is having the size of 128 bits. Okay. Then what is the capacity of the memory in bytes? Simple, just use this one. Capacity of the memory. Capacity of the memory how many? Number of words. Number of words. See, these are the basics which you should know. Number of words in the memory. Number of words in the memory. How many words are there? And each word is of what size? Okay. And word size into word size. Just have a look at this formula properly. Capacity of the memory equal to number of words in the memory into word size. Now what is this value of number of words in the memory? Observe here. System with 512 gigawords. So 512 gigawords. These many words. And each word is of what size? 128 bits. 128 bits. Now tell me, what will this be? 512. I told you initially, you should remember that. What is 512 is what? 2 raised to 9. 2 raised to 9 means 512. Okay. This one, 2 raised to 9. Next, G. What is G? See, K means 10, 2 raised to 10. 1K means 2 raised to 10. 1M means what? 2 raised to 20. 1G means what? Giga, 2 raised to 30. Okay. Into 2 raised to 30. That is what it is. Okay. Into 128 bits. If you want to convert bits to bytes, what you will do? 1 byte, you already know this one. 1 byte equal to 8 bits. Now if there are 128 bits, how many bytes it will be? Obviously just divide it by 8. 8 1s are 8, 9, 10, 11, 12, 4 remainder, 48. So 8 6 are 48. 16 bytes. Done. Now observe this one. What is this 16? 16 is what? 2 raised to 4. So 2 raised to 9 into 2 raised to 30 into 2 raised to 4. Done. Now multiply this. 9, okay, 2 raised to 9 into 2 raised to 30 into 2 raised to 4. What will it be? Just add it, okay. 9, 10, 11, 12, 13. 30 plus 13, 43. So eventually it will be what? 2 raised to 43 byte. This is what is the answer. Now, okay, will you keep that 2 raised to 40 as it is? Okay, you already know that 2 raised to 40 means what? Giga and then tera. It will be T, isn't it? Kilo 2 raised to 10 mega 2 raised to 20, giga 2 raised to 30, tera 2 raised to 40. Acha, you know that 2 raised to 40 is tera, 1 tera. So you have 2 raised to 40 here. How you can split this one? 2 raised to 3 into 2 raised to 40. Done. This is bytes, okay. Equal to 2 raised to 3 is what? 2 to the 4 is 8. 8. 2 raised to 40 bytes. Okay, 2 raised to 40 means what? This T. TB. Done. 8 TB is the answer. I hope you got it. 8 TB is the capacity of the memory. This is how you can find it. Next question. Consider a system with 64 M words and each word is having the size of 48 bits. Then what is capacity of the memory in bytes? So this time I will not write exact formula, okay. Same formula what we used earlier. I'll just write capacity equal to just to get hands-on on this 2 raised to thing, isn't it? This power thing, K, M, that notation, that representation, just to get habituated to it, I have given this problem. Capacity of the memory is what? How many words are there in the memory? 64M. Okay, 64M into 48 bits. So 48 bits, just you have to convert it into what? 64M means what? 2 raised to 6. 2 raised to 6, 64. M is what? Into 2 raised to 20 into 48 bits. 48 bits is how many bytes? See, 8 6 are 48, so 6 bytes. 6 bytes. I think you can directly multiply 6 bytes with 64. 6 with 2 raised to 6. That will be good. You just do it, okay. 24. 384. This should be the answer. 384 MB. Done. Done with this one. I'll just rub this one. Eraser. Let me get back to this pen. Okay. 384 MB is the answer. Capacity of the memory. This is how you can find it. Next question. Consider a system where 32 binary bits are used to represent all the words of the memory. Okay. You tell me. If 32 binary bits are used to represent all the words, how many words will be there? Just check this one. See, if one bit is used to represent, how many words can be possible? 0, 1. Okay, 2 words can be possible. If 2 bits are used to represent memory, then how many words can be possible? 0, 0, 0, 1, 1, 0. Okay, binary all this. 1, 1. 4 words are possible. With 2, 4. With 1, 2. With 3, 8. Okay, 2 cube is 8. Same way. If there are 32 binary bits, 2 raised to 32 words will be possible. I hope you got it. Next one. I'll just delete this one. Erase all ink on the slide. Okay, done. See, have a look at this one. Capacity will be what? Number of words in the memory. 32 binary bits are used to represent all the words, so it means 2 raised to 32 words are there. Done. Next one. Of the memory, and each word is having the size of 32 bits. See, each word is having size of 32 bits. Again, convert that bits to bytes and that work is done. Your work is done. 2 raised to 32 into what? 32 bits. 32 bits means what? How many bytes? See, 1 byte equal to 8 bits. Just divide by 8. 8 4s are 32. So, 4 byte. Done. Now, you can just 4 into 2 square. You can split this one, okay. This is 2 raised to 32. You should intuitively get it, okay. 2 raised to 2 into 2 raised to 30. 2 square means 4. 4 4s are 16. Okay, you can multiply it. 16. So 16 into 2 raised to 30. This is what you will get. 16 into 2 raised to 30. 30 means what? GB. I'll just state it, okay. 2 raised to 30 byte. Is it word or byte? Bits byte. Okay, fine. Here we converted bits to bytes, fine. Okay. 16, what is it? 16, 2 raised to 30 means what? GB. That is the answer. I hope you got it. Let's see next question. Before that, let me just rub this one. Equal to 16 GB. Done. Next question. Loading. See, Now we'll see the concept of loading, linking and address binding. Within loading, we'll see static loading, dynamic loading. Within linking, we'll see static linking, dynamic linking. Within address binding, there are different types. Compile time address binding, load time address binding and dynamic address binding, or execution time address binding or runtime address binding. Okay, let's have a look at all of these concepts one by one. Loading. See, bringing the program from secondary memory to main memory is called loading. From secondary memory, just hard disk, okay, hard disk, SSD, whatsoever it might be, from secondary memory to main memory, bringing it, RAM, is called as loading. Done. Very easy. You are just loading it. Next, types of loading. Static loading, dynamic loading. Two types. Next one. Linking. Establishing the linking between all the modules or all the functions of the program in order to continue the program execution is called as linking. Just for example, just have a look at this one. See, you have that main function. Within main function, let's say you have used printf. Wherever printf function that let's say it is present in some header file, isn't it? Which header file? stdio.h. stdio.h header file contains that implementation of printf function. Just you are connecting everything. Okay, let's say you have written some function fun, or let's say sum is the function name. You are connecting that functions. Okay, whenever you are calling that addresses. Okay, everything. You are just linking, connecting, establishing the linking between all the modules or all the functions of the program in order to continue the program execution is called as linking. Done. I hope you got it. Let's see next one. There are different types of linking: static linking, dynamic linking. We'll see this one. Loading the entire program into memory before the start of program is called static loading. So before that program starts, if you load everything, static loading, isn't it? Next one. See, inefficient utilization of memory is there because of it. Next one, program execution will be faster. Since you are loading everything at the start, okay, program execution will be faster because you are doing everything initially itself, isn't it? You are loading that entire program. You are not loading some chunks or pieces of it, okay? You are just loading that entire program before starting, isn't it? Done. If static loading is used, accordingly static linking will be applied. If static loading is used, static linking will be applied. Same case with dynamic as well. See, loading the entire program into memory on demand is called dynamic loading. So whatever is needed, just load it on demand. Load it on demand. Dynamic loading. Next one. This is what we are using, isn't it? Dynamic loading, dynamic linking. Okay. Efficient utilization of memory is there, but then it is somewhat slower. Okay. Program execution will be comparatively slower, okay, not as such slower, but comparatively slower compared to the previous one which we saw, isn't it? Compared to static loading. Next one. If dynamic loading is used, accordingly dynamic linking will be applied. Done. If static linking is used, static loading is used, static linking will be applied. If dynamic loading is used, dynamic linking will be applied. Next one, address binding. See, association of program instructions and data to physical memory locations is called address binding. Just associating that program instructions. Address binding is of three different types. First one, compile time address binding, CTAB. Next one, okay, load time address binding, LTAB. Third one, execution time address binding, ETAB. Execution means while running, isn't it? So that is why it is also called as runtime address binding. Address binding happens while it is executing, runtime, on the go, okay. Or dynamic address binding, compile time, okay. Very easy. Done before loading the program into memory, load time address binding after loading, okay. And while it is running, runtime address binding. See, very easy. CTAB, compile time address binding, done before loading the program into memory. Before it is loaded into memory, it is done. Load time address binding, obviously when it is loaded into memory, done after loading the program into memory. Next one, ETAB, execution time address binding, or RTAB, runtime address binding, or DAB, dynamic address binding. All three indicate same only. Okay, done on the runtime. That's it. It is done on the runtime. Next one, majority of the operating systems practically implement dynamic loading, dynamic linking and dynamic address binding. Okay, all Windows, Linux, everyone, okay, majority of the operating systems mostly follow dynamic loading, dynamic linking and dynamic address binding. Done with this point as well. Next one, contiguous memory management technique. See, let's see memory management techniques. Contiguous memory management technique and non-contiguous memory management techniques. These are two I mean that memory management techniques are classified in these two ways. Contiguous, non-contiguous. MMT indicates memory management technique. Okay. Next one. Within contiguous memory management technique, you have two things: fixed partition scheme, variable partition scheme. Next one. Here, paging, multi-level paging, inverted paging, segmentation, segmented paging, demand paging. Okay, lots of things are there in non-contiguous memory management technique. So for today's lecture, let's start with fixed partition scheme. Then we'll move on to variable partition scheme. Then paging. Let's see if we can cover multi-level paging as well. These three remaining points. Okay, till demand paging. Okay. We'll do it in next session. We'll take 2 sessions for memory management techniques since it is big topic. Next one. Let's see fixed partition scheme. In the fixed partition scheme, memory will be divided into fixed number of partitions. Okay, there are fixed number of partitions. Now, only one process can be accommodated in every partition. So there are lots of partitions and there are fixed number of partitions and each process can go in in one particular partition. Only one process can go. That is what is mentioned. Degree of multiprogramming is restricted by the number of partitions in the memory. So in the first lecture, I have told you about degree of multiprogramming. Okay, what is it? Number of processes present in the main memory at any point of time is called as degree of multiprogramming, isn't it? Now, see this one. Degree of multiprogramming is restricted by the number of partitions in the memory. They told, isn't it? If memory is divided into fixed number of partitions, okay, fixed number of partition. Obviously, how many partitions are there? In each partition, only one process can come. Then how many processes can come? Equivalent to number of partitions. It means what? Degree of programming, multiprogramming is restricted by that number of partitions. That's it. Done. Maximum size of process is restricted by maximum size of partition. Obviously, if let's say maximum size of partition is 500 KB, so you cannot keep 600 KB process within it. I hope you got it. Next one. Every partition is associated with limit register. There are 2 types of registers: lower limit, upper limit register. I'll draw a diagram. It will be good to understand with the help of diagram. Lower limit register, it contains starting address of the partition. Next one. Upper limit register, it contains ending address of the partition. See, just I'll draw the diagram. Just look at it carefully. If possible, you also draw along with me simultaneously. Simple. Let's say there is a request by process of size 50 KB. It is kept here. I'll just draw that fixed partitions. Okay, let's say 75 KB. Just some randomly I am putting in some values. Let's see what happens. 100 KB. Okay, next one. 350 KB. I think this, I should rub this one. Eraser. 350 KB. I'm just drawing fixed number of partitions. That's it. Very easy. Just I need to keep. Okay. 350. Let's say 60 KB. 1, 2, 3, 4, 5, 6, 7. Let's take 8 total. Just for the sake of convenience. 20 KB. 40 KB. And let's say it is 200 KB. Just randomly I have taken some values. Processes are residing into it. Okay. Let's say process P1 is here. Process P2 is here. Process P3 is here. Process P4 is present here. Process P5 is present here. Process P6 is present here. Process P7 is present here. Process P8 is present here. Now observe that, let's say process P1 went to completion, okay, completed. P1 and let's say P5, P1 and P5 got completed. These two processes got completed. It means they are no longer in that main memory right now. Are you getting it? P1 and P5 are no longer in that main memory right now. Now you tell me, if there comes another process with request, let's say 50 plus 60, what is it? 110 KB. So there came another process, let's say P9 process came, whose size is 110 KB. Will we be able to accommodate that process P9 into memory? See, we are having 50 plus 60, 110 KB memory free right now. But we will not be able to allocate P9 process of 110 KB into our memory, isn't it? Why? Because that 50 KB and 60 KB is available, but it is not available contiguously, isn't it? It is not available contiguously. So that is one of the things. Next one. Let's see one more point about this one. Okay. Now, if you observe this one, let me write this one. P10 process. Let's say P10 process arrives. P10 process arrives. It is of size 30 KB. P10 process arrives of size 30 KB. Now, will we be able to place P10 process here? Obviously, P10 process can be placed here. Because this slot is of 50 KB, we can place 30 KB process, isn't it? This 20 KB will be pending, will be remaining, isn't it? This 20 KB free, isn't it? Now, even though 20 KB is free, if another process whose size is 20 KB comes, we won't be able to store it here. Are you able to get it? Because this partition is of 50 KB and 20 KB is available, still you won't be able to place it, because in every partition only one process can be placed. That's it. Only one process can be placed. So we just place P10 process, that's it. So we won't be able to place more process. This is where the internal fragmentation comes into picture. Internal fragmentation. Internal fragmentation will come into picture, isn't it? Space is available, but still you can't utilize it. Isn't it? 20 KB is still available, but you can't just utilize it. That's it. Done. Next one, let's see variable partition scheme. Okay. In the variable partition scheme, initially memory will be contiguous free blocks. So contiguous free blocks. Next one, whenever the request by the process arrives, accordingly partition will be made in the memory. Whenever the request comes, let's say 50 KB process request, 50 KB partition done, 100 KB process request, 100 KB partition done, that way. If the smaller process keep on coming, then larger partitions will be made into smaller partitions. Done. To avoid the problem of external fragmentation, compaction technique can be used. Done. Let's see what is compaction technique after we see this example. If you have a look at this one, I'll draw it fastly. This time I'll draw it fastly. See, let's say process request, REQUESTS. This I'll draw a rough diagram. Let's say requests are of process P1 request 50 KB. P1 of size 50 KB is requesting. So we'll make a slot for P1 in the memory of size 50 KB. Okay. Okay, what is this one? This one is limit register. Okay, limit. I think I should rub it right now. It is better that I state it, not write it. Or you can write it here, maybe. This is limit register. Limit register. Lower limit register contains lower starting address. Upper limit register contains ending address of that memory slot. Done. So, see, Next process request P2. P2, let's say 100 KB. A slot got created for process P2 of 100 KB. Then I'll draw it fastly. Let's say P3 came. Let's say 150 KB. 150 KB. I think I should rub it. 150 KB. Again, P3 slot got created for 150 KB. Done. Same way, okay. Same way it will keep on happening, okay. Let's say some 30 KB, 45 KB, 70 KB, something like this, 80 KB, something like this, random. Okay, it kept on coming. There are requests by process of this particular sizes. We kept on creating blocks. Okay. Now, let's see this particular process went to completion. Let's see some other process. Here is P4, P5, P6, P7. This went to completion. Okay. 100 plus 170. Again, same problem happens here, isn't it? So here, if another process whose size is 170 KB comes in, we won't be able to store it immediately because it is not available contiguously, isn't it? 100 KB is available, 70 KB is also available. But 170 KB contiguously is not available. That is where that external fragmentation will come into picture. EF, external fragmentation. Done. External fragmentation will come into picture. Fine. So that is the issue with this one. Okay. In order to eliminate that external fragmentation, see, memory was available but not available contiguously. So what we can do, we can just move all these pages, all this process upside, so that downside free space will be available, or move all that process downside so that upside free space will be available. This technique is called compaction. Let's see compaction, okay. Moving all the process to the top or to the bottom to make the free available memory in a single contiguous place is called as compaction. Either to the top or to the bottom, we have to move it. So anyone is okay. If you move process to the top, in the bottom, there will be free available space. If you move it to the bottom, in the top, there will be free available space. Anyhow, that issue of external fragmentation will be eliminated using compaction. Okay. Next one. Compaction is undesirable to implement because it interrupts all the running process, because you will have to just move it, isn't it? It might be in usage. Next one. Let's see partition allocation methods. The 4 methods: first fit, best fit, worst fit, next fit. Let's see all these techniques one by one. First fit. Allocate the process in a partition which is first sufficient from the top of the memory. See, first sufficient partition from top of the memory. We'll keep on scanning from top. Okay, done. Best fit. Smallest sufficient. Best fit means what? Smallest sufficient. Allocate the process in a partition which is smallest sufficient among the free available partitions. See, this is first sufficient. I'll just stress on to this point, first sufficient. Here I'll stress on to smallest sufficient, this point. Smallest sufficient. To find out the smallest sufficient, it requires to search all that free partitions in the memory. Are you getting it? We'll have to search all that free partitions in the memory. Next one, worst fit. Allocate the process in a partition which is largest sufficient. Worst fit, largest sufficient among the free available partitions. To find out the largest sufficient, again we'll have to scan entire memory. It requires to search all the free partitions in the memory. Done. Next fit. The next fit is just like first fit. From the last allocation point, we'll do first fit. Done. So next fit also works like first fit, but it will search for the first sufficient partition from the last allocation point. Okay, this is important. First sufficient partition from the last allocation point. This is important. Next fit. Behaves like first fit only, but from last allocation point, we'll keep on searching it. Done. So let me draw maybe a random diagram. Consider the following memory map, okay. See, I'll just draw it fastly. I won't take a lot of time. Let's say, okay, 8 KB, already there. This is free slot, okay. This is free. Busy slot. There's something there, isn't it? Now, let's say 8 KB, 22 KB. Let's say 36 KB. 2 KB. Okay. Or let's take 36 KB here. Better to make here. Eraser. I'll change this to 11 KB. 11 or okay. Let's keep it 11. Now see, if request of process P1 comes of 16 KB, what will happen? If you use first fit, in which particular chunk or hole will you place that process with size 16 KB? From starting, you keep on checking, okay, 16 KB available? No. 16 KB available. 22 KB. You'll keep it in 22 KB slot. Are you getting it? You'll keep it in 22 KB slot because from starting itself, first fit means what? From starting itself, you keep on checking for a slot in which you can place that particular process. Done. First sufficient. This is first sufficient. If you use, let's say first fit, then what is it? Next fit. Now let's say best fit. Now what will be the best fit here? 16 KB process, 8 KB, 12 KB. Okay, this is sufficient. 2 KB. These two are sufficient. 22 KB and 36 KB both are sufficient. Among them, which is smallest sufficient? 22 KB. Here also 22 KB only. Answer. Let's see worst fit. Worst fit. Scan the entire memory, free partitions, and search for largest sufficient. Among all this, largest sufficient will be obviously 36 KB. So you will place that particular process in this particular free block. Okay. Now, next fit. So if let's say this is the last allocation point. Okay. Assume it to be last. I'll just write it. Okay. I hope it is visible. Last allocation point. Considering this to be last allocation point, where will you place the process with 16 KB using next fit? Obviously, from the last allocation point, you will just use first fit, isn't it? First sufficient partition from the last allocation point. From here, just keep on checking. Okay, 2 KB can't place it, 36 KB we can place it. So 36 KB. I hope you got it. Done with this one. Let me just erase this one. Okay, anything else to add? This one and this one. Done with this one. Okay. Let's see next one. How many successive requests of 6 KB will be satisfied by using first fit, assuming variable partition scheme? See, very easy. 6 KB request, how many can be satisfied? You refer to the same memory map, okay? Same memory map. Consider this memory map, okay, for this question also. Now, how many successive requests of 6 KB will be satisfied by using first fit, assuming variable partition scheme? See, how many 6 KB processes can be satisfied here? Only one, isn't it? 8 KB. Okay, here how many? 6 1s are 6, 6 2s are 12, 6 3s are 18, 6 4s are 24. Okay, 6 3s are 18. 3 processes can be satisfied. Got it? 6 2s are 12, so can't do it. 6 1s are 6, only one process can be accommodated here. 2 KB, less than 6 KB, don't think of it. 36 KB, 6 6s are 36, so 6 plus. So overall 1 plus 3 plus 1 plus 6, what is it? Answer 1 plus 3 plus 1 plus 6. Let me just check it. 1 3 1 6. Correct. So 6 plus 3 4 10 11. Answer 11. 5 plus 6, 11. Done. 11 successive requests of 6 KB can be satisfied using first fit. Okay, done. Next one, consider the following memory map. Okay, so just I have not drawn that diagram, I guess, deleted it. Have a look at this diagram. So this is 150 KB free space and this is 350 KB free space. And let's see what happens. What is asked? The requests from the process are 300 KB, 25 KB, 125 KB and 50 KB respectively. So these are requests from the process. Which of the following partition allocation techniques could satisfy the above request? Okay, best fit but not first fit but not best fit, both best fit and first fit and best fit, neither first fit nor best fit. So we just need to check for best fit and first fit. Let's do it for first fit. See, using first fit, what will happen? 300 KB request came, 300 KB request came. Let's do it. From starting onwards, we'll see, okay, 150 KB, we can't place it, 350, okay, 300 KB, we can place it here, 300 KB. Done. How much is free? This is occupied now. This is occupied, isn't it? This 300 KB by that particular process. 50 KB is free. 50 KB is free. Okay. 25 KB came. Here 25 KB. 25 KB. Because first fit, no. From starting onwards, you need to see. Done with this one. 25. How much is left? 125 KB is left. Next one. 125 KB. Okay. You can just place it here, 125 KB. Done with this one. And then finally 50 KB. Okay, 50 KB you can place it here. Done. So first fit works fine. We can satisfy the requests of all the process using first fit partition allocation method. So first fit is okay. First fit works properly. Done. Now let's see best fit. Now let me rub it. Okay, let me rub it. Eraser. Okay, let's see what happens in case of best fit. 300 KB, best one will be to keep it here. Okay, obviously 300. Because anyway, in 150 KB slot, how can 300 KB process be placed? Obviously not, because 150 is less than 300. We need greater than equal to 300 KB slot. So 350 KB slot, we'll place it. Done with this one. This slot completed. How much is remaining? 50 KB is pending. Now 25 KB. Will you place 25 KB process in 150 KB slot or 50 KB slot? See, best fit indicates what? Smallest sufficient. So you'll place it here. Okay. Let me just make a partition. This will be 25 KB. If it is 25 KB, you tell me. Okay. This is 25 KB. 25 KB is pending, 25 KB. Are you getting it? 25 KB is free right now here. Next one, 125 KB. We'll place it here. Nowhere else we can place 125 KB. Done. 125 KB done. And then 50 KB. Okay. See, from 50, 125 gone. How much is left? 25 KB. Now, our process of size 50 KB, we have to accommodate it. Do we have 50 KB in memory? Oh, we are having 25 KB and 25 KB. But is it available contiguously? No, it is not available contiguously. That is why we cannot accommodate that process of size 50 KB into our memory. Okay, using best fit right now. So best fit doesn't work. Okay, I hope you know this concept. This is concept of what? External fragmentation. 25 KB plus 25 KB, okay, 50 KB, our process of size 50 KB. 50 KB is available, but it is not available contiguously. That is why there is what? This indicates what? EF. EF means what? External fragmentation. Done with this one. So first fit, okay, best fit, not okay, okay. First fit, but not best fit. Option B. Done. I hope you got it. Let's see next one. Paging. From this point, I want all of you to concentrate properly. This is very important, paging. Lots of problems can be framed using this concept, paging. Okay. terminology used is as follows: logical address space or virtual address space, LAS or VAS, represented in the form of words or byte. Example 32 gigaword, 32 gigabyte, etc. It indicates what? Your secondary memory. Okay, logical address space, virtual address space. Okay, next one. In words or bytes. Secondary memory in words or bytes. Okay, logical address or virtual address. How many bits are used to represent it? Okay, represent in the form of bits. Example 24 bits, 32 bits. Logical address, virtual address in bits. Logical address space, virtual address space in words or bytes. Next one. Physical address space represented in the form of words or bytes. Example 512 kilobyte, 512 kilobyte. Physical address represented in the form of bits. See, physical address in bits, physical address space in words or bytes. Example, okay. Done. Done with this one terminology. So tell me, if logical address is 37, what will be logical address space? Very easy. Logical address space will be, I'll just do it fastly, okay. Logical address space will be what? 2 raised to 37. 2 raised to 37. With 37 bits, how many unique words can you represent? How many unique numbers can be represented? 2 raised to 37, isn't it? So, 2 raised to 37 words. What is it? 2 raised to 37 words means what? 7, I told you, 128. 2 raised to 7 means 128. 128. 30 means what? Giga words. 128 gigawords. Now, if one word is of, if one word equal to 1 byte, then it will be, logical address space will be what? Logical address space will be 128 gigabyte. 128 gigabyte. I think I should rub this one. Just a second. 128 gigabyte. Done. Next one. Okay. If logical address space is 256 megaword, what will be logical address? See, very easy. Logical address space equal to 256 megaword. What does it mean? 256 means what? 2 raised to 8. 2 raised to 8. Mega means what? 2 raised to kilo mega. 20. 2 raised to 20 word. So it is effectively what? 2 raised to 28 word. So obviously 2 raised to 28 words. How many bits are needed? Logical address will be 28 bits. With 28 bits, 2 raised to 28 unique words can be represented. Fine. We can address 2 raised to 28 numbers. Fine. Done with this one. Let's see next one. Physical address 46 bit. What will be physical address space? Just have a look at this one. Physical address space will be equivalent to 2 raised to 46 word. What is it? 6 means what? 64. 64. 2 raised to 40 means what? 2 raised to 40. See, 10 means K, 1K. 2 raised to 20, 10 is 1K. 2 raised to 20, 1M. 2 raised to 30, 1G. 2 raised to 40, 1T. Tera. TB. TW. Let me just write it W. Just a second. Tera word. Now, if one word equal to 1 byte, then physical address space equal to 64 tera word. Array, terabyte. This is byte. Here it is byte. Okay. I'll rub it. Just a second. TB. Done. Next one. Last one. This is last problem. Physical address space is 64 kilobyte. What will be physical address? If physical address space is 64 kilobyte, what will be physical address? Obviously, see, physical address, see, I'll write it. Physical address space equal to 64 kilobyte. What does it mean? 64 means what? 2 raised to 6. 2 raised to 6. Kilo means what? 2 raised to 10 byte. What is it? 2 raised to 16 byte. So to represent 2 raised to 16 bytes, okay. 2 raised to 16 unique words. How many bits are required? 16 bits. Physical address will be 16 bits. Done with the numerical part. Let's see theory part once again. Okay. Paging. The technique of mapping that CPU generated logical address to physical address is called as paging. Let's see how it happens. Paging is implemented in the hardware level. See, general scenario, if you observe this one, logical address space and physical address space. Logical address space will be comparatively bigger, isn't it? Your secondary memory will be much bigger than your RAM, isn't it? If your RAM is of let's say 8 GB, and most probably your secondary memory will be around maybe 1 TB. So obviously 1 TB is greater than 8 GB. So that is why logical address space is greater than physical address space. That is why logical address is also greater than physical address. So this is the general scenario. Logical address is greater than physical address. Okay. General scenario. Okay. Typically this is what you can see. Okay. RAM can be 4 GB. It means 32 bits will be needed to represent it. ROM can be of 1 TB. So 40 bits will be needed to represent all the words of that ROM. So 32 is less than 40, okay, or so this is what logical address. This will be logical address. This will be physical address. So obviously physical address will be less than logical address. Most of the time this is what happens. Okay, that is why I mentioned the title general scenario. Okay, next one. See, LS is divided into equal size pages. Number of pages, logical address space by page size. So okay, I will tell you all this via diagram. Don't think too much right now. Okay, no need to memorize everything. I'll just you concentrate. Okay, next one. Physical address space is divided into equal size frames. Number of frames equal to physical address space by frame size. Note, page size equal to frame size. I'll explain all these points using this one particular example. Okay. Logical address equal to 13 bits, physical address equal to 12 bits, page size equal to 1 kiloword. So if logical address, see, if logical address, this is logical address space. If logical address is of 13 bits, what will be logical address space? It will be 2 raised to 13 byte. What is it? 2 to the 4 to the 8. 8 KB. Done. Next, physical address is of 12 bits. So what will be physical address space? Let me draw physical address space. This is physical address space. 2 raised to 12 byte. So what is it? 2 raised to 12. 4 KB. Done. Page size is of 1 kiloword. Okay. Page size. Logical address space is divided into pages. These are pages. Logical address space is divided into pages. Page size is what? 1 kilobyte. What is mentioned? 1 kilo word. Okay, word is mentioned. So let us consider everything as word. Are you getting it? Since here word is mentioned, let us consider everything as word. Let me erase this one. I didn't saw that word. Just a slight correction. Word. So you please be careful, okay, while solving problems. 1 kilo word. 1 kilo, this is word, okay, not byte. 1 kilo word means what? 2 raised to how much? Eraser. 1 kilo word equal to 2 raised to 10 word. Done. So if this entire block size is 2 raised to 13 word and this small chunk is of 2 raised to 10 word, how many such chunks can be there, isn't it? This is logical address space. Logical address space is divided into pages. Each page is of size 2 raised to 10 words. Now what will be the number of pages? Obviously, divide this by this. 2 raised to 13. What is 2 raised to 13 by 2 raised to 10? 2 to the 4 to 2 raised to 3, which is equal to 8. 8 pages. 8 pages will be there. I hope you got it. Okay, how many pages will be there? 8 pages total. See, I mentioned it. 8 pages. Now, you tell me what will be number of frames in physical address space. 2 points I mentioned earlier. First point, logical address space is divided into pages. Next point, physical address space is divided into frames. Let's see frames. Third point, page size and frame size both are same. So if page size is 1 kiloword, frame size will also be 1 kiloword, no? Isn't it? 1 kiloword. What is it? 2 raised to 10 word. Now if it is 2 raised to 10 word, this entire chunk size is 2 raised to 12 word. How many such frames will be there? 2 raised to 12 by 2 raised to 10. What is it? 2 raised to 2, which is equal to 4 frames. Done. So you got the answer as 4 frames. You got 4 frames. Easy, isn't it? 8 pages, 4 frames. That is what you will get. Next one. What else can be shown from this one? See, we'll come to the point of page table. Number of pages in page table. We'll draw something like this in upcoming slides. We'll create a page table. Now for each process, we'll have to create a page table. Why we have to create it? All that theoretical points are explained in the upcoming slides. So let's see page table when we'll encounter that page table theory. Okay, let's see this one. As of now, this is done. Okay, this is done. Number of pages you got. From logical address and physical address and page size, what all points did you get? First, logical address space. Next, physical address space. Number of pages, number of frames. These 4 points you got automatically. 2 more points you'll get. First one, this one. See, number of pages in page table is equivalent to number of pages, 8. Okay, number of entries in page table is equal to number of pages in logical address space. So that also you got. Okay, to represent 4 frames, page table contains frame number. Okay, page table contains frame number. This is another point. Now if it contains frame number, it has to address all that frames, isn't it? How many frames are there? 4 frames are there. To represent 4 frames, how many binary bits are required? 4 means 2 square, 2 bits. So page table entry size is 2 bits. Done. Next point you got 8 entries in page table entry size 2 bits. Now what is page table size? From this you will get page table size. Tell me, what is page table size? 8 into 2 bytes, 2 bits. 8 entries in page table, each entry is of 2 bits. So 8 to the 16, 16 bits. It means how many bytes? 8 to the 16, so 2 byte. Done. So page table size also you got. From these 3 points, what all things you got? Logical address space, physical address space and page size. From these 3 points you got first one, logical address space. Second, physical address space. Third, number of pages, isn't it? Logical address space is divided into pages. Logical address space is divided into pages. Number of pages, you got it as 8. Next one, 4th point, number of frames you got. Physical address space is divided into frames. 4 frames you got. 4th. 5th point, number of entries in page table, that is what you got. 6th point, page table entry size. Since page table entry consists of frame number, I told you this point, page table entry will consist of frame number. So in order to address that 4 frames, we need 2 bits. That is why page table entry consists of 2 bits. You got this one as well. And finally, page table size. Just multiply 8 by 2 bits, isn't it? Number of entries in page table into page table entry size. Done. That's it. So many things you got. 1, 2, 3, 4, 5, 6, 7. From these 3 points, you got 7 different things. So that is why I feel that diagrammatic representation is essential. With this diagrammatic representation, you can learn faster, isn't it? Next point. Okay. Some of the pages from the logical address space will be brought into the physical address space. Okay, let's talk in detail about pages. Just have a look at this one. Page size is 1 kiloword. They have mentioned page size as 1 kiloword. What does it actually mean? Just have a look at this one. 1 kiloword means what? See, they mentioned page size equal to 1 kiloword. What does it mean? There are 1 kilo words into the memory, into the page, isn't it? It means there are 1k words. 1k means what? 2 raised to 10, isn't it? 1k indicates what? 2 raised to 10 words. Okay, if there are 2 raised to 10 words starting from 0, what will it be? 0 to, tell me fastly, 0 to 2 raised to 10 minus 1. This will be words. That's it, that's it. So very easy, just have a look at this one. If this is entire page, it will be divided into words. 0th word, first word, second word, third word, so on till what? 2 raised to 10 minus 1. 2 raised to 10 minus 1, this word. I hope you got it. Now you tell me, how many bits are required to represent it? If there are 2 raised to 10 words, how many bits do we need? 10 bits. All zeros to all ones. Do it. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. 10 zeros. Now 1 means what? 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. Next one. 2 means what? 1 0, isn't it? In binary. 0, 0, 0, 0, 0, 0, 0, 0, 1, 0. 3 means what? 1 1. 0, 0, 0, 0, 0, 0, 0, 0, 1 1. Done. Last one. 2 raised to 10 minus 1. What will be the last one? All zeros to all ones in binary. So 10 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Done with it. Page size 1 kilo word. It means there are 1k words. Each word is having what? Inside each word there will be instructions. I1, I2, I3, I4, let's say this so on. There will be actual instructions will be present, isn't it, inside this word. So I'll just state it explicitly. It will be good if I state it explicitly. These are actual instructions. What are these? Actual instruction. ACTUL. Actual. INSTRUCTIONS. And instructions of the process. Done. Done with this one. So you got to know what is meaning of that page size 1 kilo word. Okay, each one is of one word. One word. 1 kilo word. 1 kilo words are there. Each is one word. Fine. Done. Done with it. Let's see next one. Now again theoretical points. Okay. Some of the pages from the logical address space will be brought into physical address space. Okay. Done. Actual instruction will be present inside every word of the process. That is what I mentioned. See, actual instructions of the process are present inside that word. Actual instructions will be present inside every word of the process. Whenever paging is applied, page table has to be maintained. Whenever that paging is applied, page table has to be maintained. Okay. Page table, number of entries in the page table is same as number of pages in logical address space. I explained that also. In that previous example, I explained it. When I drawn that page table, number of entries, what I took? In logical address space, number of pages was 8, so 8 entries I took. That only. Number of entries in the page table is same as number of pages in logical address space. Next one. Page table equal to address translation table. Alternative name, okay, page table is also called as address translation table. That because why it translates address, isn't it? You want to go to a specific page. Within that page table entry will consist of frame number. Okay, from that page number you got frame number. Translation happens. Okay, page table equal to address translation table. Done it. Frame number equal to translation bits. You can just note it. Done. Logical address consists of P and D, where P is, okay, this is just terminology. Okay, have a look at this one. See, let's say this is processor P, it generates logical address PD. Okay, logical address, how many bits? Okay, whatsoever it might be. Let's say logical address. Or let's take that example which we took earlier. Which was that example? Let's take this example. logical address is 13 bits, physical address is 12 bits, page size is 1 kiloword. Based on this example, let's frame entire thing. Okay, once again, let's do it. See, 13 bits. I will draw the diagram very properly. You please watch carefully. Okay, I will draw. What is this one? See, this is CPU. This CPU generates logical address. CPU generated logical address. 13 bits logical address. Logical address is of 13 bits, isn't it? Why? Because logical address space is 13 bit. Logical address is 13 bits. It is given, isn't it? 13 bits logical address. It is divided into P and D. P will point to that page. D page offset. Okay. Now let's say D is okay. We got this one, isn't it? I'll just draw fastly. 8 pages we got. 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 2, 3, 4, 5, 6, 7, 0 to 7. 0 means what? 0, 0, 0. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Done. This is logical address space which was of 2 raised to 13 word, and this is of 2 raised to 10 word, and number of pages we got is 8 pages. Done. Next one. What we got? Next one. I think we got physical address space with what? 4 frames, isn't it? In that previous problem. 1, 2, 3, 4. 4 frames. 0, 1, 2, 3. 0 means what? 0, 0. 1 means what? 0, 1. 2 means what? 1, 0. 3 means what? 1, 1. Done. This is physical address space of 12 bits. Physical address space is 12 bits, which was mentioned. It means physical address space will be 2 raised to 12. 2 raised to 12 word. Done. This page size, frame size same, so 2 raised to 10 words. Number of frames will be how much? 2 raised to 12 by 2 raised to 10, 2 raised to 2. It means 4 frames. 4 frames are there. Now, next one. I told you about page table also. Page table, see. Number of entries in page table. Tell me, what is number of entries in page table? It is equivalent to number of pages in logical address space. 8 pages, so 8 entries. 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 2, 3. I'm just drawing it fastly, okay. 4, 5, 6, 7. 0 indicates what? 0, 0, 0. 1 indicates 0, 0, 1. 2 indicates 0, 1, 0. 3 indicates 0, 1, 1. 4, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. This is page table. Done. Page table entry will be of how many bits? See, since frame number will be present in page table entry, 4 frames are there. In order to represent 4 numbers, you need 2 bits. So 2 bits only. Let's say these are empty. Let's say these are empty. I think I should use some other color. It is becoming uniform. Eraser. Let me change the color. Okay. Let's say something like this is there. Okay. 0, 1, 1, 1, 1, 0. Let's say, which one is remaining? 0, 0 is remaining. It means what? Page number 6 is present in frame number 0, 0. Okay. Page number 6, P6 is present here. Are you getting it? P6 is present at 0, 0 location in frame. P4 is present at 1, 0. 1, 0 means what? 2. P4. At 2. Page 2 is present at 1, 1 location. Okay, it means what? This. P2. This location. Page 0 is present at 0, 1. 0, 1 means what? This one. P0. Done. So, if you are referring to a particular page, there are 8 pages. In how many bits can you represent a page? If there are 8 pages, you need 2 cube 8. So, 3 bits to represent each page. So, in order to represent a page, you need 3 bits. Within a page, word is of, page size is 2 raised to 10 words. To represent a specific word, you'll need 10 bits, isn't it? So this page offset will be of 10 bits. I hope you got it. Why there are 3 bits here, why there are 10 bits. Okay, this is not here there won't be 3. In binary, 3, third, page number 3. So, I mean, you got it. It will be like, if I want to refer to, let's say if I want to refer to page 4. See, have a look at this. If I want to refer to page 4, what will here be? 4 means what? 100. These three bits will be here. In that because logical addresses, there are bits, isn't it? 3 bits. Which are these 3 bits? 100. Now D, within it, let's say D can be anything, okay, 10, maybe 00000000011, something like that. Third word we want to access. Now next one. Within this, what you got? 10. Okay, it is present in 10 means what? Second frame. So from here you got this one. Frame number and that offset. Frame offset. From here you got this one. This will be of 2 bits only. 10 means what? 2 bits. This will definitely be of 10 bits. 10 bits. Done. So if you observe this one, what is it? This and this both are same. Done. That's it. This is how that address translation is taking place. If you observe this one, what is this? This is 12 bits physical address. Just have a look at this one. Logical address 13 bits, 12 bits physical address. Logical address 13 bits, 12 bits physical address. You saw the conversion, how it happened. This is how it happens. This is the entire working. Okay. Logical address is divided into P and D. P indicates page number. In which particular page we have to go. I mean, processor wants to access which particular page. D indicates what? Within that particular page, which word you want to go. Page offset, done. F indicates what? Frame number. In which particular frame that particular page is present. F, done. D, within that particular frame, which, okay, what is that particular word location which you want to access? That frame offset or page offset, same only actually. Done. Done with this one. Okay, let's see next one. I already told you all these points. Next one. See, this one, this was what I wanted to mention. 3 bits, 10 bits. Okay, logical address consists of P and D. That notation I explained you. P indicates number of bits required to represent pages of logical address space. Obviously, why 3? Because there were 8 pages. In order to represent 8 pages, we want to go to specific page, isn't it? So, number of bits required to represent pages in logical address space. That is what P will indicate. 3 bits are required. That is why 3 is there. Or page number in bits. Done. Next one. D. Number of bits required to represent page size. Page size 2 raised to 10 word. So 10 bits are required. So that is why I mentioned 10 here. D. Word number of the page or page offset. So there are multiple names. Okay. Going to a particular page. Within that particular page, going to a specific word. Page offset. Okay. Page number, page offset. Something like that. Fine. Done. Physical address consists of F and D. Same. Somewhat same only. Somewhat not exactly same. See, this is F. This is D. What does F indicate? Okay, F will be 2 right now. Then D is 10. As per our previous problem. Okay, as per our previous problem. F indicates what? In which particular frame you want to go. In which particular frame that particular page is present. That is what F indicates. F, number of bits required to represent frames of physical address space. So since you are pointing to a frame, number of frames, how many number of frames are there? 4 frames are there. In order to represent particular frame, how many bits are required? That is what is F, isn't it? So for 4 frames, how many bits are required? 2 square is 4, so 2 bits are required. That is why I mentioned 2 here. Number of bits required to represent frames of physical address space. Next one, or frame number in bits. Done. D. Okay, D same both where. Okay, be it frame offset or page offset, both mean same only. Okay, D. Number of bits required to represent frame size. D. Word number of the frame. A frame offset. Okay, done. In bits. Page offset in bits, frame offset in bits, both are same. D. Okay. Next one. D. Number of bits required to represent page size. Okay. That is same. Okay. Frame size, page size, all this same. Okay. Because okay, pages are brought from logical address space to physical address space. Because that are same only, isn't it? Copy pasting is being done. So exactly same. So page size will be same as frame size, isn't it? Got it? Done. See, this is what is happening. Let's say 011 page you want to access. It means what? Third page. Third page. Within that third page, which particular word you want to access? 101, it means what? 4 plus 1, 5. Fifth word you want to access. Third page, fifth word you want to access. Where that third page is present in, let's say 10 means second frame. So second frame, that conversion will be done and this will be same. So this entire thing, logical address conversion to physical address, this entire thing is done by MMU, Memory Management Unit. This is paging work, okay. This is called paging, Memory Management Unit, okay. The technique of mapping CPU generated logical address to physical address. The technique of mapping CPU generated logical address to physical address is called paging. I hope this concept of paging is crystal clear. I explained you with example, each and everything in details. Done. Whenever the process is created, paging will be applied to the process and page table will be created. Okay. The process will be divided into pages. Okay. And the pages will be brought into memory, isn't it? Process can be big, isn't it? That is why it can be divided into pages. For each particular process, a separate page table will be created. See, whenever the process is created, paging will be applied on the process and page table will be created. You take your time to read it carefully. If you feel that the pace is somewhat fast, you take your time, read it carefully. Whenever the process is created, paging will be applied on the process and page table will be created. Base address of the page table will be stored in the process control block. In the first lecture I mentioned about process control block. Context of the process is stored where? In process control block. Done. Paging is with respect to every process. Every process will have its own page table, already mentioned. Done. Page table of the process will be stored in the main memory. Note. So there is no external fragmentation in case of paging. Internal fragmentation will exist, but it will exist in last page. Okay, and it is considered as P by 2. Okay, just have a look at this one. Internal fragmentation IF may exist in the last page and it is considered as P by 2 where P is page size. So maintaining page table is considered as overhead for the system. I think now the points of memory overhead comes into picture. See, page table is something which we maintain extra, isn't it? That is why it is overhead. Overhead means burden, okay? Burden onto the system. So memory overhead is maintaining page table. Apart from that, that internal fragmentation is also there. Internal fragmentation of paging. So internal fragmentation is considered as page size by 2, I mentioned earlier. So see this memory overhead. Memory overhead equal to page table size plus internal fragmentation in paging. Memory overhead is page table size plus internal fragmentation in paging is what? Page size by 2. Done. This is very important. Remember it. Done with this one. I hope everything is visible clearly. Just read it, go through it once. Okay. Memory overhead is page table size. Why? Maintaining page table is itself burden onto the system, isn't it? Burden overhead. Okay. Plus internal fragmentation in paging. Internal fragmentation is paging is considered as page size by 2. That is why I mentioned page size by 2 here. Done with this one. Okay. Page table entry definitely contains frame number. Okay. In that page table entry, there will be frame number, isn't it? But apart from frame number, there will be other things as well. See, page table, we drawn here. If you look at all the diagrams which I have drawn, here I have drawn logical address space, here physical address space, here page table. A page table, we are pointing to physical address space, isn't it? It means that frame number has to be present. So page table entry consists of frame number definitely, but apart from that, some other things are present, some other bits are present. What are these? Valid, invalid bit, okay, page protection bits, reference bit, dirty bit, etc., etc. See, have a look at this statement carefully. Note, page table entry definitely contains frame number, but sometimes along with the frame number, it may also contain additional bits like, just I'll mark it, valid or invalid bit or present bit. Next one, dirty bit or modified bit. Next one, reference bit. Next one, page protection bits or permission bits. A frame number will definitely be present, but apart from frame number, all these things Might be present, okay. It is not that it will definitely be present, might be present, okay. It may also contain, okay. Done. Let's see this one. See, page table entry. This is frame number, valid or invalid bit or present bit, dirty or modified bits. I have mentioned it here, okay. Reference bit, page protection bit or permission bits. Done. You please have a look at this entire diagram carefully. I'm just going outside the frame. You please have a look at this diagram. Read it carefully, okay. Just read it carefully. Done. Now let's see next point. Valid, invalid bit or present bit. This bit is used to identify whether the page is available or not available in the main memory, isn't it? Present bit. See, if present bit is 0, what does it mean? If present bit is 1, what does it mean? 1 means it is present, 0 means it is absent. It is not present, isn't it? See, very easy. Valid or invalid bit 0, it means what? Page is not present in memory. Valid or invalid bit 1, page is present in the main memory. Okay, so size will be what? 1 bit. So because 0, 1, 0, 1, just if you want to represent only 2 numbers, 1 bit is, isn't it? If you want to represent 2 numbers, isn't it? 1 bit is sufficient. That is why size is 1 bit. Done. Dirty bit or modified bit. This bit is used to identify whether the page is modified or not modified by the processor while accessing the page as a part of the execution. If it is modified, 1. If it is not modified, 0. See, just have a look at dirty bit or modified bit. If dirty bit or modified bit is 0, it means what? Page is not modified. If it is 1, it means page is modified. Very easy, very easy. Size is also 1 bit. 2 numbers you are representing, okay. With 1 bit you can represent 2 numbers. So size will be 1 bit. Okay, I mentioned it here. Size 1 bit. Next one. Dirty bit is a dirty bit in a page. Okay, dirty bit in a page for a page table helps avoid unnecessary writes on the paging device. Hence, dirty bit helps for performance optimization. Just okay, this is very important. Okay, if dirty bit is 0, just have a look at that yellow color. Okay, from here we bought that page from logical address space to physical address space. If dirty bit is 0, it means what? That page is not modified. I told you dirty bit 0 not modified. Dirty bit 1 modified. If it is not modified, you need not override this one. So here I drawn line, but I just mentioned cross here. Are you able to see it? Cross means no need to overwrite it. Okay. But in case if it is modified, the dirty bit will be 1. If it is 1, here whatever changes are made here, you need to make that same changes here, isn't it? So just while you need to overwrite, that's it. That is why it is mentioned. This way, if you maintain dirty bit, sometimes you may not write it unnecessarily. Okay. Avoid unnecessary writes on the paging device. That is what it will help, isn't it? Avoid unnecessary writes. By maintaining that dirty bit, in this case you didn't write, in this case you wrote it. Done with this concept. Next one, reference bit. This bit is used to identify how many times the page is referred by the processor. So as such, how many times it is referred. It can be any number of times. So a specific number of bits are not present. Okay, just have a look at this. Size cannot be specified. It depends on the number of references. Okay, done. That is size can't be specified. Any specific number can't be said directly. Done. Page protection bits or permission bits. These bits are used for the protection and security from unauthorized access. Done. So straightforward everything. Whatever I mentioned till here, I hope everything is crystal clear till now. We have taken examples as well. Just have a look at this one. Consider system which has logical address of 27 bits. I'll just write that given data here. Okay. It is better to write given data here. Logical address is what? 27 bits. Physical address 21 bits. Physical address 21 bits. See, page size is given 4 kiloword. Page kilobyte. Memory is word addressable. Okay, word addressable memory, that is also given. Word addressable memory. Next one, calculate the number of pages and number of frames. What we need to do? Number of pages. See, sometimes number of this hashtag is represented for number of pages. We need to calculate equal to question mark. Next one, number of frames equal to question mark. This is what we need to calculate. Let's calculate it. Okay, very easy. You please concentrate. If you feel inactive at any point of time, just drink water, because drinking water increases your activeness level. Or maybe you can eat chocolate. Okay, I have listened from somewhere. Okay, some source. Either drinking water or eating chocolate increases your activeness level. So better to do one of them. Okay, but please concentrate. Be active. Next one. Let's solve it. Okay. Logical address 27 bits. I have not left space for solving it or what. Okay, I think you must have mentioned this one. I'll just, okay, I'll erase everything. Erase all ink on slide. Let me draw it. See, very easy. What is this logical address space? Now, logical address is given as what? 27 bits. So 2 raised to 27 word. Word addressable. Word addressable. So 2 raised to 27 word. 2 raised to 27 word. Not byte. Okay. Word addressable is mentioned, isn't it? That word can be anything if it is specified. Okay. Physical address space. Physical address 21 bits. So just draw physical address space. Okay. Physical address space. Now if it is 21 bits, 2 raised to 21 word. Done. Word addressable given, word mentioned. Page size is 4 kiloword. You tell me 4 kiloword means what? 4 means 2 squared. K means what? 1K is 2 raised to 10. 2 square into 2 raised to 10, 2 raised to 12. 2 raised to 12 word. This is what 2 raised to 12 word. 2 raised to 12 word. Page size is same as frame size. So here also 2 raised to 12 word. This is basic maths. This entire chunk size is 2 raised to 27. This single, okay, it is divided into 2 raised to 12 smaller chunks. Okay. So how many such chunks will be there? So to be specific, let me say it explicitly. Logical address space is divided into pages. Each page is of size 2 raised to 12 word. So how many such pages will be there? Obviously 2 raised to 27 by 2 raised to 12. What is 27 minus 12? So 27 minus 12, it is 15. 2 raised to 15 pages. Got it? Correct? 12 plus, okay, 27 correct only, no? 2 raised to 15 pages. Done. Next one. If physical address space is divided into frames, 2 raised to 21 word physical address space is divided into 2 raised to 12 word frames. How many such frames will be there? You tell me. Very easy, very easy. 2 raised to 21 by 2 raised to 12. So 21 minus 12, just do it. So 8, 9, 9. 2 raised to 9 frames. 2 raised to 9 frames. Done with this one. So the question was to calculate number of pages and number of frames. We calculated it. How many pages? Answer me fastly. Number of pages. Number of pages equal to 2 raised to 15. What is it? 2 raised to 15 means what? 5, 32. Okay. In 1 means what? 2 raised to 10 means what? K. 32K. 32,000 kind of. 32K pages will be there. Number of frames. Next question. Number of frames. 9. 2 raised to 9. 2 raised to 9. It means what? 2 raised to 9 is what? 512. 512. 512 frames. Done with this one. Let's see next one. Performance of paging. So this is very important. You please concentrate. Main memory access time MMAT. In order to access that main memory, you need the notation MMAT is considered as M. Okay. Next one. The page tables are stored in main memory. That page table, if you are accessing page table, you are accessing main memory. That way you think. Because page tables are stored in main memory, isn't it? Whenever you access page table, main memory access time, you take it into consideration. Done. Next. Then the formula for effective memory access time is as follows. M plus M to M. What is this first M? You tell me. Accessing page table. This one is for page table. Access page table. This M is for access actual page. Actual page. In order to access that page table M, and once you access, you got everything. In order to access that actual page, just M. Done. This is without TLB. You will get to know that concept of TLB right now. Okay, with TLB, effective memory access time will be somewhat different. You need to take into consideration TLB hit ratio, TLB miss ratio. Okay, TLB access time as well. Done. Let's see. Okay, the TLB, translation look aside buffer, is added to improve the performance of paging. TLB is a hardware device implemented using associative register. It is a hardware device. Okay, TLB access time will be very less as compared to main memory access time. That is why we'll be accessing TLB first. First access TLB. Then if that page is present, directly access that particular page. If not, access page table. From that page table, go to memory. Then done that way. TLB contains frequently referred page numbers and corresponding frame numbers. Done. TLB access time C, TLB hit ratio X, then formula of effective memory access time EMAT is as follows. So this is the formula. X, what is X? TLB. So this way, I think you won't be able to understand it this way. It is better to understand via diagram, isn't it? With diagram it will be good. See, I will just draw it. You please look here carefully. What will happen? See, you will go to TLB, you will access TLB. If there is hit in TLB, it means you can directly access that actual page from physical address space. Hit. If there is hit, now this green is for hit. Let's say another color. Which one? Let's say blue. If there is miss in TLB, what will happen? You access TLB, but there is miss in TLB. You will access page table now. Now, afterwards you will access that actual page. Are you getting it? See, if there is hit in TLB, you will directly access that page. So, TLB hit rate X into, since you saw TLB, the time to see TLB, C plus actual page M. I hope you got it. What is it? X C plus M. You got this one. TLB hit ratio, TLB access time, main memory access time. What is this? TLB hit ratio. What is this? TLB access time. What is this one? Time to access. Time to access actual page. Done. 1 minus X means what? If X is TLB hit ratio, 1 minus X will be what? TLB miss ratio. Now 100% minus X, 100% means once. 1 minus X, miss ratio. Okay. This is what? Let me change the color. What is this? Okay. This is what? TLB miss ratio. Done. What is C? C is again TLB access time. TLB access time. Just like main memory access time is M, TLB access time is what? Just C. Just notations only. Okay. Next one. What is this M? You look here. If there is miss in TLB, see this blue color line. You saw TLB. If there is miss in TLB, if there is hit, you directly access the page. If there is miss, you will access page table first. And then you will access actual page. So this M is what? To access page table. This first M is what? To access page table. Time to access page table. This next M is what? Time to access actual page. Time to access actual page. Done. Very easy. It is very easy. I hope you got to know this entire concept of effective memory access time. Done. Done with this one. Okay. Green color for miss. Okay. Green color for hit. This one for 1 minus X. Let me just state it explicitly. Or okay. X hit 1 minus X. I hope this will clarify everything. If there is hit, you directly access page. If there is miss, you access page table and then access exact page. Done. Consider a system which has main memory access time of 100 nanoseconds, TLB access time of, okay, just MMAT. M is what? Given data. M equal to what? 100 nanoseconds. M equal to 100 nanoseconds. TLB access time. C equal to what? C equal to 20 nanoseconds. And TLB hit ratio 95%. TLB hit ratio X 95%. So 95% means what? 0.95, isn't it? What is the EMAT, effective memory access time, with TLB and without TLB? Okay, next is multi-level paging. So let me do it here. Okay, you calculate it. I'll just write a formula. Okay, first one, without TLB, what will happen without TLB? See, effective memory access time, this will be what? Tell me fastly. Effective memory access time will be what? Without TLB, if TLB is not there, you will first see page table and then see actual page. Done. M plus M, 2M. Done. 2M, what is it? 2 into what? 100. 100 nanoseconds equal to 200 nanoseconds. Done. Done without TLB. Now see with TLB, what will happen? With TLB, effective memory access time equal to effective memory access time, EMAT equal to, what is effective memory access time? Just have a look at it. See, TLB hit ratio, take it, X, what is it? 0.95. I think I should mention formula first, then I'll put the values, that will be good. Just put that values, let me write formula, X, TLB hit ratio. If there is hit, you have actually seen TLB, isn't it? So write C as well. See, if there is hit, you will access that actual page, plus M. Main memory access time to access that page, isn't it? Because it is present in what? Physical address space, isn't it? To access physical address space, main memory access time, isn't it? Main memory only. Done. Plus 1 minus X. If there is miss in TLB, X means TLB hit ratio, 1 minus X TLB miss ratio. C plus 2M. C plus 2M. Why 2M? C means what? TLB. So even if there is miss, you have actually seen TLB. No, just take it into consideration that TLB access time. And then if there is miss, you will access page table first and then actual page. So 2 times. Page tables are stored in main memory itself. That is one of the points I have mentioned. So M plus M, main memory access time taken 2 times, 2M. Done. Just substitute it and you will get the answer. Nothing more, difficult. Okay, 0.95. I'll not be calculating it. You do it at home. Okay. C. What is C? 20. 20 plus M is 100. M is 100 plus 1 minus 0.95. What is it? 0.05. Don't write 0.5 in hurry. Otherwise, everything will be wrong. Okay. 1 minus 0.95 is 0.05. Okay. 20. TLB access time. 2M. What is 2M? 2 into 100. So 2 into 100. Done. You calculate it, you will get the answer. Okay, with TLB and without TLB. This is without TLB 200 answer, and with TLB just calculate it. Okay, you just do it. Okay, what is it? You just do it. Okay, done. Done. Let's see next one. Multi-level paging. To avoid the overhead of bringing large size page table into main memory, the concept of multi-level paging is used. See, I told you earlier, page table is present in main memory. Now, what if that page table entries are too much and that page table doesn't fit in a page? Because if it is stored in main memory, it is stored in where? Frames itself. What if that page table doesn't fit in a frame? We'll have to do further paging. Till the point of time that particular page table fits in a frame, we'll have to do further paging. Just have a look at this one. To avoid the overhead of bringing large size page table into main memory. Large size page table into main memory. The concept of paging is used. In the multi-level paging, paging will be applied on the page table. And instead of bringing entire page table into memory, pages of page table will be brought into memory. That is important, isn't it? Let's see with example, you'll get to know more. Or, okay, we can do this thing, okay. Just maybe simple example I'll share. Not with values, just visualize it. This is logical address space. I've drawn it at this side, logical address space. It consists of what? Pages. Now, this one is physical address space. It consists of what? Frames. Now, let's see page table. In general, what will happen? This page table, the entries will be how much? Equivalent to number of pages. Entries will be equivalent to number of pages. These are number of frames. Hashtag frame. Just I am writing hashtag for number of, okay, frames. So, entries in page table will be same as number of pages, okay. Okay, this E is not properly written. Entries in page table equal to number of pages. And this, all these are page table entry. This is what? This is page table entry. Let's say page table entry size, whatsoever it might be. Done. Now, observe one thing carefully. Why? Okay. Observe one thing carefully. Why do we want to use multi-level paging? Just have a look at this one. If this entire page table doesn't fit in one frame, what will happen? Let's say if it fits in multiple frames, this frame, so on till this last frame, then we will do further paging. Are you getting it? We'll create another page table. Okay, this is page table of page table. This is page of page table. This entire thing was page table. These are pages of page table, isn't it? This is equivalent to page size, okay. Page size. This is equivalent to page size. Page of page table. These are page of page table. And based on these pages, their starting address we mentioned here in another page table. So what is this? Page table of page table. This is what is happening. I hope you are getting it. This is the concept of multi-level paging. Very easy concept. So this is outer page table or first level page table. This is inner page table or second level page table. I hope it's clear. Done with this one. First, what will happen? First, we will see here. From this, we will see. Okay, whichever page of page table it is pointing will go into that page table. Okay, and then we'll see that particular page table and then look ahead. That way, it will happen. Let's see next the procedure. Okay, I think I should delete it. Let me delete everything. Erase all the ink on the side. Okay, P1 number of bits required to represent pages of page table. P1 page number of page table. Okay, see, initially what we did, logical address was this one, isn't it? Logical address P and D. Now P will be further splitted into P1 and P2. P1, P2 and D. This is logical address only. Okay. Splitted. From this you will come to a point where you will get that frame number, in which frame that particular thing is present. What is it? F and D. What is this? Physical address. So that is the procedure which you will have to follow. From PD to P1, P2D to FD. Done with this one. Very easy. Just have a look at this one. See, we will read all this after seeing diagram. First we will see diagram. Okay. Just have a look at this diagram. CPU generated logical address, 32-bit logical address, let's say. Okay. D is, let's say, 12 bits. P, 20 bits. Now, if you observe this one, P splitted in P1, P2, 10, 10. Okay. Why 10? Why 10? Observe here. What is page? It is okay. Anywhere it is mentioned? One word is mentioned here. Okay, forget. Just look here. Overall view. Have a look at it. Logical address space. Logical addresses consists of P and D. P indicates what? Which page you want to go. D indicates what? Within that page, which offset you want to go. Done. This is clear. Next one. P is split into P1 and P2. P1 indicates what? The page table of page table entry in which you have to go. For example, if 4 is mentioned, we'll go here. See, have a look at this one. We went here. This way it happened, isn't it? Now, after going here, here will be what? Which address will be present here? Here will be the address, starting address of page table. So this page of page table, this address will bring this particular page of page table into memory. Now, once it is brought, we'll use P2. We'll use P2 to get to that specific page. Third location. Okay, what will be present here? Once page table is done, we'll get into frame number. Here we'll get F, that particular frame number in which that particular page is present. This is how from P to P1, P2 to F. The PD to P1, P2, D to FD. That is how conversion will happen. I hope you got that entire scenario. Let me just read out the points which are mentioned here. Page of page table, inner page table, second level page table. Page table of page table, outer page table or top or first level page table. First level page table, second level page table, outer page table, inner page table. Done. Another point. This stores what? Base address of inner page table or second level page table. If there is one more level, it will store base address of this particular page table, isn't it? Next one. Stores, this slot stores frame number of actual page. Done with this one. I hope everything is clear in multi-level paging. Next one. We are about to end the lecture, few more minutes and then done. Just have a look at this one. In the multi-level paging, when the paging is applied on the page tables, the last level page table which we get is first level page table. See, we applied paging, isn't it? Just have a look at the diagram. I think I deleted that diagram, isn't it? See, this last level page table is actually called first level page table. So there are lots of pages. This will point to a page of page table. This will point to page of page table. This will point to page of page table. Like that, there are lots of page of page tables, isn't it? So in the multi-level paging, when the paging is applied on the page tables, the last level page table which we get is called first level page table. Done. Now next one. In the multi-level paging, when the paging is applied on the page tables, then first level page table entry. That first level page table entry will contain what? Base address of second level page table. Now second level page table entry will contain what? Base address of third level page table. That third level page table entry will contain base address of fourth page table. Okay, fourth level page table. So on it will continue, isn't it? So on. The final page table entry contains frame number of the actual page, because finally that we want that frame number F, isn't it? Because PD should finally be converted to FD. That logical address should finally be converted to physical address. It should happen, isn't it? With the help of that page tables, we are doing it. Okay, be it single level, be it two level, be it three level, be it multi level, anything. Okay. If it is not single, it means it is multi. Be it two level, three level, all are multi-level page table. Done with this one. In the multi-level paging, see, few theoretical points are there, and last point, then we'll end the lecture. Please concentrate. In the multi-level paging, when the paging is applied on the page tables, then whatever may be the levels of the paging, all the page tables will be stored in main memory. All that page tables will be stored in the main memory, irrespective of whatever levels are there. Done. That is the point. In the multi-level paging, when the paging is applied on the page tables, then whatever may be the levels of paging, whatever may be that levels of paging, all that page table entries contains frame number only. Okay, done. All page table entries contain frame number. Done. Why frame number? Okay, just have a look at this one. Have a look at this diagram. This is containing frame number. This is containing frame. Why is this containing frame number? Okay. this entire thing is also present in main memory, isn't it? In a frame, starting address of that frame. Frame number only, everywhere there is frame number only. I hope you got that point. Okay, next one. Next one. In case of multi-level paging, till when do we have to perform paging? Okay, till when do we have to perform paging? Very easy. So till this point, till this page table size is less than equal to page size. We'll keep on doing further paging till the point we encounter that page table do not exceed page size. If it exceeds page size, again perform paging, done. So till it don't exceed page size, perform paging. Until we encounter the following situation, page size is less than equal to, page table size is less than equal to page size. Because page tables are stored in main memory and page tables should fit in that frame. If it is stored in main memory, it will be stored where? In frames. So page table should fit in a frame. If that page table should fit in a frame, its size should be less than equal to page size or frame size, whatever you take it, okay. Frame size, same only. Page size is same as frame size, okay, so no need to worry. Same only, okay, nothing different. Done. You remember this one, this is important, okay, remember it. Next one. I mean, no need to remember also, it is logical, okay, no need to memorize, it is logical, understandable. Till when will we do paging? Till that particular situation is encountered. Until that page size is less than equal to, page table size is less than equal to page size. Performance of single level paging, performance of 2 level paging, performance of 3 level paging, and then done with this lecture. Let's do this one. Okay, terminology use main memory access time M, TLB access time C. I told you main memory access time I used M notation, TLB access time C notation, TLB hit ratio X notation. Okay, and then we have to find effective memory access time EMAT. With TLB, without TLB. Okay, let's see without TLB. Single level page table. Let's do it first. Okay, next one. Okay, EMAT without TLB. What will happen? See, very easy. Okay, next one. Okay, see. Without TLB, no? So let me just write it. See, I'll just draw a rough diagram. This is logical address space. This is physical address space. And this is page table. Without TLB, what will happen? Tell me fastly. You will access the page table and then you will access actual page. You will access the page table, then you will access actual page. So EMAT will be what? EMAT will be M plus M. What is this M? To access that page table. What is this M? To access that actual page. M plus M, 2M. Done. I am doing it with visualization. You please concentrate. You will love this concept, okay? I am doing it with visualization. Just concentrate properly. Next one. EMAT with TLB. Just have a look at this one. Same, somewhat similar diagram. Just draw logical address space. Just draw physical address space. Just draw page table. Just draw a TLB. Translation look aside buffer. Okay. So what will happen in this case? See. With TLB, you need to consider TLB hit ratio, TLB miss ratio, all these things into consideration. See, if there is hit in TLB, you will access that page directly. If there is miss in TLB, okay, green indicates, let me write somewhere, green color indicates TLB hit. Okay, let me change the color. Which color you want to take? Tell me fastly. Let's say blue. Okay, if there is miss in TLB, you will access that page table and then you will access that actual page, whatever it might be. Blue color indicates what? Tell me fastly. TLB miss. Done. TLB access time C, main memory access time M. Okay, done. So what will be the formula? Tell me. EMAT, effective memory access time, equal to X, TLB hit ratio, C plus what? M. TLB access time plus main memory plus that time to access actual page plus if it is not hit, it is miss, 1 minus x. Then what is C plus TLB you access, isn't it? Plus M plus M. What is it? M is what? To access that page table. Next M is what? To access that actual page. M plus M is what? Just 2M, isn't it? So you can just write it X C plus M plus 1 minus X C plus 2M. Done with this one. EMAT is this one. EMAT with TLB. This is the formula. I hope it's 2 minutes. Okay. So we are about to end. Just 2-level paging and 3-level paging. 4 diagrams, and then we'll end it. We'll end it in 5 minutes. 5 minutes itself. Okay. Just 2-level paging. Consider 2-level paging. The same terminology. We are using M, C, X, and all this. Okay. We just need to find EMAT without TLB. Let's do it for 2-level paging. Just have a look at it. If there is 2-level paging, just see this. This is level 1 page table, level 2 page table. Then this is physical address space. This one is what? Logical address space. Logical address space. See, level 1 page table, level 2 page table, or let's say page of page table, page of page table, page table of page table. See, what will happen in this case? Without TLB, you will access this one, then you will access this one, then you will access that actual page, whatever it is present. Done. Here also same thing happens, isn't it? You are accessing that actual page. So what is it? M plus M plus M. 3M. See, EMAT is what? Effective memory access time is what? 3M. Done. I hope you got this formula. Done with this one. Next one. With TLB, same diagram. With TLB, what will happen? I'll just draw fastly, very fastly. About to end the lecture. Just few minutes. Logical address space, physical address space. This is page of page table, page table of page table. See, green color. Acha. We just forgot to mention TLB. This is TLB, translation look aside buffer. Now, green color indicates what? TLB hit. If there is hit in TLB, what you will do? You will directly access that particular page. Done. You will directly access that particular page. If there is miss in TLB, okay, green color is for hit. Okay, green color is for TLB hit. Let's see next color. Okay, let's take blue only. Okay. If there is miss in TLB, what will happen? You will see that page table. Page table of page table, then you will see page of page table, and then you will see that actual page. What is happening? M plus M plus M, 3M. I hope you got it. So effectively, what will be that formula? EMAT. You just have a look at this one. EMAT what? TLB hit rate, X. TLB access time, C, plus time to access that actual page, M, plus 1 minus X, TLB miss rate. Okay, if X is hit rate, 1 minus X is miss rate. Okay, time to access the TLB, C, TLB access time. And then if there is miss, M, all this in main memory itself. Main memory access time is M. Okay, I'll mention here, blue color indicates TLB miss. Done. So 3M, that's it. M, 3M. Done. This is formula. And last point of this session, performance with 3-level paging. Just I'll mention that formula with small diagram and we are done. Very small diagram, okay? Just bear with me. Just ending in 2 minutes only. So this is logical address space. This one is physical address space. This is first level page table. First level page, not first level, this is third level actually. Third level page table. This one is second level page table. This one is, okay, first level page table. Okay, now what will happen? You tell me fastly. Without TLB, we will access first level page table first, then second level page table, then third level page table, then we'll access that actual page. Are you getting it? What is it? M, because page tables are also stored in main memory itself, isn't it? That is what we have seen. So M, 1, 2, 3, 4. So EMAT will be what? EMAT will be what? 4M. Done. Done with this one. Last slide of the session. EMAT with TLB. See, I'll just draw the diagram once again. With TLB, what will happen? Logical address space is there. Here is physical address space. Okay. 3 boxes. Let me draw it fastly. 1, 2, 3. And then this TLB. TLB first level page table. Second level page table. Then third level page table. Okay, done. So if you observe this one, let me take green color. Green color for what? TLB hit. You access TLB, you access actual page. Done. You access actual page. Done. So green color is for what? Green color indicates TLB hit. Done. Let me just do TLB miss. You access TLB. Okay. If there is miss, you will access first level page table, then you will access second level page table, then you will access third level page table, and then you will access that actual page. So what is it? 4M. Okay. So formula. Okay. Blue color for what? TLB miss. Blue color for TLB miss. Translation look aside buffer miss. Now let me write that entire formula. Effective memory access time will be what? Effective memory access time. Yes, I wrote it EMAT. I hope it is visible. Okay. Effective memory access time equal to what? If there is hit, what you will do? You will access that actual page. You access TLB, you access actual page. If there is miss, 1 minus x. If there is miss in TLB, 1 minus x. Then you will access first level page table, then second level page table, then third level page table, and then that actual page. 1, 2, 3, 4, 4M. C plus 4M. Done. Done with this one. So if you generalize this entire concept to n level page table, what will happen? If you generalize this entire concept to n level page table, just tell me the formula. That's it. You just tell me the formula. EMAT will be what? EMAT. You tell me. So for, see, if you look here, for single level page table, what is EMAT? 2M. For 2 level page table, 3M. For 3 level page table, 4M. For n level page table, n plus 1M. Done. N plus 1M. N level page table. N indicates number of levels. Okay. Done. Done with this formula. Next one. EMAT with TLB. Just have a look at this one. Okay. EMAT equal to, I hope it is visible. Okay. X, TLB hit rate. TLB access time. Okay. Let me just, okay. Let me just delete. Okay. What happened? Erase. Something happened. Okay. Let me just, fine. Erase. EMAT with TLB, what will it be? X, C plus M plus 1 minus X into. If there is TLB miss, what will happen? You will access TLB and then what will you access? Tell me fastly. You compare this with previous one. Single level page table, 2M, C plus 2M. 2 level page table, C plus 3M. 3 level page table, C plus 4M. So 3 level page table, 4M. So n level page table, n plus 1M. N plus 1 into M. Done. Done with this particular thing and done with today's class. I hope you have understood each and everything and you enjoyed this lecture actually. Why? Because I have shown you everything with visualization, with the diagrams. You just have a look at the diagrams. Okay. I have mentioned each and everything beautifully with diagrams. So not just with formula. Okay. I have made it intuitive. So that's it for this video. We have in fact seen lot of things. Okay. Lot of things. All this you need to remember, okay? All this you need to remember, K, M, G, T, P, all these things, okay? Just remember all these things. Loading, linking, address, binding, everything. Just remember it. Contiguous. Just, okay, in this contiguous, okay, in this fixed partition scheme, you remember one point, okay? Here there will be internal fragmentation. Why? Why? Because you won't be able to store another process even though there is empty slot here. Why? Because in a particular partition, this is called as, okay, this is what? Partition. P-A-R-T-I-T-I-O-N. Partition. Or it is also called as chunk. C-H-U-N-K. Chunk. Or it is also called as whole. Done. Okay, you remember it, okay. There will be internal fragmentation, okay. All this limit register, variable partition scheme, everything done. First fit, best fit, next fit, worst fit, everything done. Okay, we just saw examples as well. Okay, example as well, paging done, everything done. I hope you liked this entire session and you understood each and everything from beginning to end. I hope this was interesting. That's it from my side. Thank you so much. Bye.